At 10 minutes and 38 seconds past 4, on the afternoon of August 14, 2003, the power grid of the eastern United States stopped behaving like a machine. In the next 2.5 minutes, 508 generating units at 265 power plants shut themselves down. 50 million people across 8 states in the province of Ontario lost power. Nothing exploded. Nobody attacked anything. Every piece of equipment did exactly what it had been designed to do. And for a full hour before it happened, the whole thing was still preventable. Nobody acted because nobody could see it. In a control room in Ohio, the alarm system had stopped working nearly 2 hours earlier, and it had not told anyone. This is the story of how a grid dies. Not in a storm, not under attack, on a calm, warm Thursday in a room where nothing was beeping. To understand what went wrong, you have to understand what a power grid actually is, because it is not what most people picture. There is no reservoir, there is no tank. At the scale of a continent, electricity is not stored. Every watt being consumed right now is being generated right now somewhere, by a machine that is spinning. Which means supply and demand are not balanced daily or hourly. They are balanced continuously forever to within a fraction of a percent. The measure of that balance is frequency. In North America, the grid runs at 60 cycles per second, generates slightly more than is being consumed, and the spinning machines speed up, consume slightly more than is generated, and they slow down. Every generator on the eastern half of the continent is locked to the same rhythm. Thousands of turbines from Florida to Manitoba turning in step. That rigidity is enormous. On August 14th, moving 1,000 megawatts, the output of a large nuclear reactor shifted the frequency of the entire eastern interconnection by about 0.03 of a hertz. That is the system working. It is so stiff that losing a power plant barely registers. The problem is what that stiffness means when it finally lets go. Because the same physics that keeps thousands of machines in step also means they fail in step. A grid does not fail one piece at a time. It fails the way a rope fails, every strand carrying a little more until the next one goes. Everything that follows is that sentence, playing out over 3 hours and 56 minutes. FirstEnergy served 2.5 million customers across northern Ohio, Cleveland, Akron, Toledo. Its control room did not look out at the grid, it looked at a screen. Somewhere out there were thousands of miles of conductor, hundreds of substations, dozens of generating stations. None of it visible, none of it audible. The operator's entire sense of the system arrived as data, over wires, into a computer called an energy management system. That system had one job above all others, to tell them when something changed. A line trips, a breaker opens, a voltage sags, and an alarm fires. Alarms were not a convenience. They were the sense organ. Take them away and an operator is not slower. They are blind in a room that looks exactly the same as it did a minute ago. FirstEnergy's system had been installed in 1995. It had a state estimator, which builds a mathematical picture of the whole network from raw measurements. It had contingency analysis, which asks the essential question: if the next thing fails, do we survive it? The contingency analysis had been unreliable since installation, so they ran it by hand. On the afternoon of August 14th, investigators concluded it was probably running and was not consulted at any point. There was no map board. There was no simulator training. FirstEnergy had never experienced a major disturbance and had no formal preparation for recognizing one. And there was one more absence, which is the whole film in a single sentence. The alarm system had no alarm for itself. Above the utilities sits another layer, the reliability coordinator, watching a wider region than any single company can see. For Northern Ohio, that was the Midwest Independent System Operator in Carmel, Indiana. Their most important tool is the state estimator. It takes thousands of live measurements, flows, voltages, breaker positions, and reconciles them against a model of the network. If the measurements and the model disagree, the estimator will not solve. At about 12:15, it stopped solving. A line in Indiana had been switched out, and the model had not been told. An analyst found it, corrected the model, and got a good solution. To troubleshoot, he had turned off the automatic trigger that re-ran the estimator every 5 minutes. He did not turn it back on. In the words of the investigation, thinking the system had been successfully restored, the analyst went to lunch. At 2:02, a line called Stewart Atlanta tripped on a tree 200 kilometers away in a different company's territory under a different reliability coordinator. Electrically, it was irrelevant to Ohio. It changed nothing about the flows there. But it was in the model, and it was now wrong. So the tool built to watch Northern Ohio was broken by a line that had nothing to do with Northern Ohio, not by changing the power flows, but by breaking the picture. It would not run properly again until 4:04, 2 minutes before the cascade. At around 14:02, the alarm software inside FirstEnergy's control system stalled. The investigators describe it precisely. The process began working on one alarm event and never finished. It did not crash. It did not report an error. It kept running and quietly stopped producing output, while new events piled up behind it until the buffers overflowed. General Electric, who built the system, later described the underlying flaw as two processes contending for the same data structure, both able to write to it at the same instant. A window measured in milliseconds. In 8 years of operation, it had never happened before. Engineers audited roughly 1 million lines of code and could only reproduce it by deliberately inserting delays. But the mechanism matters less than the shape of the failure. It failed silently, and a silent failure of an alarm system is worse than a loud one, because the absence of alarms is indistinguishable from the absence of problems. At 2:41, the primary server failed. The system switched to its backup. 13 minutes later, the backup failed too, because the stalled application had moved onto it intact. This is the part engineers should sit with. Redundancy protects you against a component breaking. It does not protect you against a deterministic software state, because that state travels with the software. 2 servers, 1 bug, both dead. Screen refresh degraded from 1 to 3 seconds to as long as 59 seconds per screen. And in the control room, the chart printers kept rolling. The pens held the last valid measurement and drew it forward, straight, across the paper. The investigation's own word for it was flat lining. Nobody noticed. Meanwhile, and this is the cruelest detail in the entire report, the rest of the system was working. FirstEnergy's computers kept sending accurate, up-to-date information out to neighboring utilities. The outside world could see FirstEnergy's grid. FirstEnergy could not. At 3:08, the support team completed a reboot. The diagnostics reported every process running normally. The alarms were still dead. Nobody told the control room. Investigators found no indication that support staff informed the operators when they began work or when they finished. Later, an operator was asked about it. From his experience, he said, it was not unusual for alarms to fail. The fact that they failed did not surprise him. Now the physical world starts to fail, and nobody in the room knows. At 5 minutes past 3, a 345 kilovolt line called Harding-Chamberlain touched a tree and locked out. Here is the detail that reverses the story most people have heard. That line was not overloaded. It was carrying 44% of its rating. At 44%, it was not hot, and it was not sagging unusually. The tree had simply grown into it. The conductor was 46 feet and 7 inches above the ground. The tree they cut down afterwards measured 42 feet, with burn marks nearly 36 feet up the trunk. The reliability coordinator did not find out this line was gone until after the blackout was over. 27 minutes later, Hannah Juniper failed the same way, at 88% of its rating, witnessed by a FirstEnergy tree crew standing 3 spans away. 1,200 megavolt amperes of power now had to find another route. And in a grid, power does not ask permission. It redistributes itself instantly, according to the impedance of every available path. At 41 minutes past 3, the third line, Star South Canton, locked out at 93% of its emergency rating. 3 lines in 36 minutes, all from trees, none of them overloaded. The investigation was blunt about what that means. FirstEnergy's 5-year trimming cycle was, in its words, consistent with industry practices. And then, although FirstEnergy's vegetation management practices are within common or average industry practices, those common industry practices need significant improvement. The indictment is not of one company, it is of an entire industry, because at that moment, the reliability body had no standards or requirements for vegetation management or right-of-way clearances at all. Meanwhile, somebody was trying to tell them. American Electric Power, whose territory bordered FirstEnergy's, had its own instruments. At 2:30 they called. FirstEnergy said it had seen nothing at its end. At 19 minutes past 3, they called again. This time with a confirmed relay operation and a technician physically standing at the substation. FirstEnergy restated that it had received no alarms and saw no problem. 1 minute later, American Electric Power made a decision that is worth stating plainly. They decided to treat their own fault recorder data as a fluke. That is what a broken alarm system does. It does not just blind one control room. It exports its blindness to everyone who trusts it. From the moment the first line tripped, FirstEnergy had roughly 1 hour. The investigation is unusually specific about this. If 1,500 megawatts of load had been shed in the Cleveland-Akron area before 6 minutes past 4, the blackout could have been averted. 1,500 megawatts. Out of 61,800 that eventually went dark, 2.4% cut deliberately would have saved the rest. Earlier, it would have taken even less. Before 20 to 4, 500 megawatts would have been enough. Nobody shed a watt, not because anyone refused, because nobody knew there was anything to shed. And through that hour, the phone kept ringing. The Perry nuclear plant sat on FirstEnergy's system near Cleveland. Its operator called 3 times. At 3:30, still bouncing around pretty good. I've got it relay tripped up here, so I know something ain't right. FirstEnergy's reaction in the transcripts. It's got to be in distribution or something like that, or somebody else's problem. But I'm not showing anything. At 42 minutes past 3, I'm still getting a lot of voltage spikes and swings on the generator. I don't know how much longer we're going to survive. At 46 minutes past 3, it's not looking good. We ain't going to be here much longer, and you're going to have a bigger problem. At the same time, 42 minutes past 3, an operator finally said it out loud. Nothing seems to be updating on the computers. I think we've got something seriously sick. That is 88 minutes after the alarms died. and investigators found no indication he told any of the other operators. The two desks in that room sat across a hallway from each other, kept separate handwritten logs, and had no procedure for briefing each other. The West Desk operator had known about the alarm failure since 2:15. The East Desk operator found out at 4:15. By 3:50, FirstEnergy was driving people out to substations in cars because they did not believe they could see them with their data. And they never declared an emergency. The shift supervisor told his manager it looked as if they were losing the system. No emergency was declared because for most of that afternoon FirstEnergy did not know its system needed one. At 5 minutes and 57 seconds past 4, a line called Sammy Star tripped. There was no fault on it, nothing had touched it, no tree, no equipment failure, no lightning. It tripped because of the way it was being protected. A distance relay guards a transmission line by continuously dividing the voltage it measures by the current it measures. That ratio is impedance. A short circuit somewhere down the line looks like a sudden, specific drop in impedance, so the relay watches for that signature and opens the breakers. The relay has zones. Zone 1 covers most of the line and acts instantly. Zone 3 is backup. It looks well beyond the line and waits a second or two before acting in case somebody else's protection fails. Zone 3 is the one that mattered. By 6 minutes past 4, Sammy Star was carrying 2,850 amps, 130% of its emergency rating. The voltage at the Star substation had fallen to 91% of nominal. Reactive power on the line was almost 10 times what it had been that morning. High current, low voltage. Divide one by the other, and you get a low impedance, the exact signature of a distant short circuit. The relay could not tell the difference between a fault it was built to catch and a line simply working far too hard. So it opened. And here is the sentence the investigators wrote, which is the thesis of this entire film. The relay operated as it was designed to do. There was no malfunction, no defect. A piece of equipment measured the world correctly, applied its rules correctly, and in doing so removed the last strand holding northern Ohio to the grid. From here, human beings are spectators. Over the next 4.5 minutes, 13 more major lines opened on Zone 3 relays, not because they were faulted, because the power displaced by each failure loaded the next one, and each relay in turn read overload as a fault. The investigation's verdict is that those relays did not cause the blackout. They accelerated it. They acted so quickly that they impeded the natural ability of the electric system to hold together and left no time for any operator to intervene. At 38.6 seconds past 4:10, northern Ohio's last connection east opened, and the grid stopped being a network. Power swept counterclockwise around Lake Erie, pouring into Detroit, 3,700 megawatts, from a path that normally carried a few hundred. A second later, it reversed. In half a second, a swing of 5,800 megawatts. Frequency, which had held within a few hundredths of a hertz all afternoon, tore apart. Detroit spiked to 61.7 hertz, then fell at 2 hertz per second. Generators began to slip out of step, physically losing synchronism with the machines they had been locked to for years. At 45 seconds past 4:10, a 500 kilovolt line in New Jersey opened, and the entire Northeast separated from the rest of the continent. No operator did that. No operator could have. The pieces that were left were islands, each with its own frequency, each with too much generation or too little. New York split east from west. The eastern half fell below 58 hertz and shed 7,000 megawatts automatically. Con Edison dropped more than 40% of its load. Western New York went the other way. Trapped hydro generation with nowhere to send it drove the island up to 63.4 Hz and tripped 5 nuclear units on overspeed protection. Ontario fell to 56 Hz and lost 22,500 megawatts, including Toronto, Hamilton, and Ottawa. By 13 minutes past 4, it was over. But look at the map, because there is one more thing in it. New England did not go down. Neither did most of Pennsylvania, New Jersey, or the Eastern Interconnection behind them. They survived for a reason that is almost poetic. In the path of that surge, their relays measured the same enormous currents, but their voltages were higher because those utilities ran with more reactive reserve. Higher voltage divided by the same current gives a higher impedance. Higher impedance stayed outside the relay's trip zone. The light stayed on where the voltage was healthy enough that the protection could still tell the difference between a fault and a very bad day. The joint investigation named 4 causes. FirstEnergy and its regional council failing to understand how fragile the Cleveland-Akron area was, inadequate situational awareness, inadequate tree trimming, and the failure of the reliability organizations to provide effective diagnostic support. 7 violations of reliability standards were identified. FirstEnergy was fined nothing. Not because anyone excused it, because no fine was legally possible. 4 months after the blackout, the Reliability Council's own board wrote it down. In the absence of enabling legislation, it lacks legally sanctioned authority to enforce compliance with its reliability rules. The rules were voluntary. They had been voluntary since 1968, when the industry created the council after the last great northeastern blackout. For 35 years, grid reliability in the United States ran on peer pressure. That ended slowly. In August 2005, the Energy Policy Act created a new section of the Federal Power Act, giving a regulator the power to certify a standards body and enforce its rules. In July 2006, that body was certified. In March 2007, 83 standards were approved. And on the 18th of June 2007, 3 years and 10 months after the blackout, those standards became mandatory and enforceable. For the first time, the American grid was run under rules you could be fined for breaking, up to $1 million a day when the law was written. Among them was a standard for transmission vegetation management. It exists because in 2003 there was no tree standard at all. And to see what changed, compare 2 numbers. In 2008, a blackout in Florida cut power to part of one state. The utility responsible paid $25 million, the largest reliability penalty ever imposed. FirstEnergy, for 50 million people, paid nothing. Same country, different decade. The only difference is that by then there was a law to break. There is one last detail, and it is the quietest one. Ontario lost 22,500 megawatts that afternoon. Toronto went dark. But reliability standards had already been mandatory and enforceable in Ontario since May of 2002, more than a year before the blackout, and 5 years before the United States caught up. The gap in the law was American. Ontario was simply downstream of it. The thing worth taking away is not that a tree touched a wire. Trees touch wires constantly. It is that for nearly 2 hours, a room full of competent people were told, continuously and convincingly, that everything was fine, by a system that had already stopped looking. The grid did not fail in seconds. It failed over 3 hours and 56 minutes in a room where nothing was beeping.